For over a century, global industrial dominance relied on raw, bulk manufacturing. Today, competitive advantage is no longer found at the macro scale, but at the atomic level. At 10 to the negative 15th meters, human perception fails completely. We have to rely on mathematical models to calculate and control forces we will never see with the naked eye. Pioneers like Homi J. Bhabha recognized that these theoretical equations were the blueprints for a nation's independent technical capability. This shift from simply using materials to designing them atom by atom is the new baseline for advanced research and development. Look at transcontinental pipelines or massive civil engineering projects. When these structures fail, traditional inspection requires invasive excavation, leading to massive downtime and environmental risk. Industrial engineers solve this by deploying specific radioisotopes. Because these unstable atoms release energy as they decay, they act as penetrating tools that see through solid matter without damaging the structure. By using gamma-ray scanning like an industrial X-ray, technicians detect hidden structural voids deep inside concrete and metal before they reach a breaking point. This diagram shows a cross-section of a pipeline. By injecting beta-emitting radioactive tracers into the flow, tracking teams can pinpoint the exact location of a microscopic fracture across hundreds of kilometers of pipe. Deploying these specific isotopes allows for the precision optimization of the global industrial engine. Many environments, like the complete darkness of deep space or the intense pressures of the ocean floor, create an energy bottleneck where conventional renewables and fossil fuels fail. Nuclear fission solves this limit underwater because it is an anaerobic process. It requires no atmospheric oxygen, allowing military submarines to remain submerged and undetected for months at a time. This schematic details a radioisotope thermal electric generator, or RTG. Inside the core, plutonium-238 undergoes natural alpha decay, continuously radiating thermal energy that is converted directly into a steady electrical current. Because plutonium-238 has a half-life of roughly 80 years, it provides the longevity required for deep space. The Voyager spacecraft launched decades ago, and its nuclear fuel source is still keeping it operational in the interstellar void. The faint signals powered by those nuclear engines are still being captured here on Earth, proving that persistent mission reach is possible without solar power. By mastering atomic decay, a nation can decouple its presence from environmental constraints and maintain operations in the most hostile regions of the solar system. We see a similar increase in efficiency when we move to the nano realm, the space strictly defined between 1 and 100 nanometers. At this microscopic threshold, materials no longer follow the trillion-atom rules of bulk behavior. Instead, they experience size-dependent quantum effects that change how they react to their environment. This visualization demonstrates what happens when a single solid cube is mathematically split into 1,000 smaller ones. The total volume remains identical, but the exposed surface area explodes. Because more atoms are exposed to their surroundings, the material becomes highly reactive. This is why famously inert bulk elements like gold become potent catalysts for high-tech industrial applications when ground to nanoparticles. Physical size also dictates optical properties. By adjusting the exact nanometer size of a particle, engineers can force the same material to emit entirely different frequencies of light, creating the vibrant, high-resolution colors seen in QLED displays. Descending to the nanoscale turns static materials into customizable tools for industrial dominance. In traditional medicine, many treatments are designed for a general impact, which often results in collateral damage to healthy tissue. But biological building blocks like DNA and hemoglobin operate at the scale of 2 to 5.5 nanometers. To interact with them effectively, our medical tools must operate at that same scale. Scientists are now engineering nanomedicines designed to chemically target and destroy individual tumor cells while flowing harmlessly past healthy structures. Moving from general impact to localized intervention changes the basic mechanics of treatment. By repairing matter at the molecular root, medicine stops being a blunt instrument and becomes a precise biological fix. Large-scale nuclear integration often faces two major hurdles: massive capital costs and the legal delays of land acquisition for traditional power plants. Small modular reactors, or SMRs, offer a way to bypass these bottlenecks. Because they are factory-built and installed on-site, they offer a faster path to energy independence. This diagram visualizes the primary technical barrier to entry: isotopic separation. Because isotopes like uranium-235 and uranium-238 are chemically identical, separating them requires complex physical processes based purely on minute weight differences. Mastering these complex atomic and molecular calculations allows a nation to build advanced hardware platforms like the pushpak reusable vehicle. Controlling the nucleus and the nanolattice offers a way to decouple a nation's power from global supply chains, securing its position from the deep ocean to the edges of the solar system.